In this video, we will look at solving systems of linear equations by graphing. First, let's go through a bit of background information, and we'll use what we already know about graphing linear equations in two variables. Let's take these two equations for our example. We have lots of ways of graphing linear equations. I'll choose to set up a table of ordered pair solutions. Starting with y equals 3x minus 1, I'll choose some values for x, plug that value into the equation, and find the value of y. Let's start with x equals 0. Putting 0 in place of x in the equation, we see that y equals 3 times 0 minus 1. 3 times 0 is 0, so y equals 0 minus 1, which is negative 1. So we have our first ordered pair solution at 0, negative 1. We know that a single linear equation in two variables will have an unlimited number of solutions. And when we're graphing, we want to find at least 2 points. So let's extend this table and choose another value for x. Let's choose x equals 2. Substituting 2 in place of x in the equation, we have y equals 3 times 2 minus 1. That's 6 minus 1, y equals 5. And our next ordered pair solution, 2, 5. Here are those two ordered pair solutions written out. X equals 0, y equals negative 1 is the first solution. X equals 2, y equals 5, the second solution. And if we plot these 2 points, we will be able to see the line that makes up the graph of this equation. Going over to our next equation, I will choose to first solve this equation for y. To isolate y, first we need to undo this 2x. It's a positive 2x, so we will subtract 2x from both sides. It will get rid of this term on the left side, leaving just negative 2y. On the right side, we do not have like terms. We cannot combine these two terms. The negative 10 is just a number, a constant, but this term has a variable, negative 2x, so they're not like terms. We will be in the habit of putting the variable term first, so we'll write negative 2x minus 10. The next step to solve for y, divide every term by negative 2. That will leave us with positive y. This term here, negative 2 over negative 2 equals positive 1x, or just positive x. And negative 10 divided by negative 2 equals positive 5. Now that the equation is solved for y, I will make a table similar to what we did with this equation. We'll choose a value for x, start with x equals 0. Substituting 0 in place of x, the equation becomes y equals 0 plus 5, and 0 plus 5 equals 5. So y equals 5 when x equals 0. Next we'll choose x equals 2, so y equals 2 plus 5, y equals 7. So we have two ordered pair solutions for this equation, 0, 5, and 2, 7. So let's clear this space out and begin to make the graphs of both equations. First, let's start with y equals 3x minus 1. We can plot the point 0, negative 1. Let's label these axes, x and y. There's the point 0, negative 1. Next, the point 2, 5, from the origin horizontally 2 on the x-axis, up 5 vertically, and there's our point 2, 5. If we connect these points with a straight line, we have the graph of this equation. And we want to know that this line is made up of all the different ordered pair solutions to this equation. Like here's another point on the line, one that we did not find. What are the coordinates of this point? From the origin, we would go back 2 and then down 7. It's the ordered pair negative 2, negative 7. It's another point on the line, so it must be another solution to this equation. We can check that out if we go back to our table form and put a negative 2 in place of x. We should be able to see that y equals negative 7. Substituting the negative 2 in place of x, y equals 3 times negative 2 minus 1. So y equals negative 6 minus 1, and that does equal negative 7. So just a reminder that the line is representing all the other ordered pair solutions to this equation. We only needed to find 2 points to see exactly where the line would go on the graph, and any other point on the line is also going to be a solution to the equation. Now let's go to our other equation. First, we're plotting the point 0, 5. It's the y-intercept because x equals 0. So horizontally 0 and vertically up on the y-axis to positive 5. There's the point 0, 5. Next, the point 2, 7. Horizontally 2, up 7. There's the next point on the line. We'll draw a straight line right through those points. And again, a reminder that any other point on this line must also be a solution to this equation. This ordered pair is negative 4, positive 1. So in this equation, if x equals negative 4 and y equals positive 1, the equation is true. Let's check that out. 2 times x, so 2 times negative 4, minus 2 times y, so there's minus 2 times 1, will it equal negative 10? Let's simplify the left side. 2 times negative 4 is negative 8, minus 2 times 1, that's minus 2. Does that equal negative 10? And it sure does. Negative 8 plus negative 2, or if you see it as negative 8 minus 2, the same thing either way, it does equal negative 10. So we've shown that the equation is true when x equals negative 4 and y equals positive 1. And we know that it is a solution because it is another point on this line. So the next question is, what about this point right here? Which line is it on? Would you say that it's on this green line, or is it a point on the purple line? If it's on the green line, we know it's a solution to this equation. If it's on the purple line, we know it's a solution to this equation. And since this is the point exactly where those two lines cross or overlap, that is really a point that is on both lines. So it must be a solution to both equations. And we can see that these two lines cross only at this point. It's the one solution that is working for both equations. We have an unlimited number of ordered pair solutions on the green line that are all solutions to this equation, y equals 3x minus 1. An unlimited supply of ordered pair solutions on the purple line that are all solutions to this equation, 2x minus 2y equals negative 10, but only one point where the two lines cross that is a solution to both equations. So when we're dealing with a system of equations, two or more equations working together, the solution to the system would be the solution that works for each individual equation. So when we solve systems of equations by graphing, we graph each equation individually using the exact same strategies that we've been using so far to make graphs of linear equations. And the solution to the system, which is the solution to all the equations, is the point where the two lines cross, because it's actually a point that's on both lines. So it's a solution to both equations, and that makes it a solution to the system. So what is this ordered pair? From the origin, we would go to the right 3 and then up 8. So the ordered pair 3, 8, which represents x equals 3 and y equals 8. Let's just check that it really is a solution to both equations. Starting with y equals 3x minus 1, let's make another table and let's use x equals 3. And we should be able to see that when x equals 3, y equals 8. Let's place 3 in place of x in the equation. Y equals 3 times 3 minus 1. So y equals 9 minus 1, and that is 8. So definitely 3, 8 is a solution to the first equation. Does it also work for the second equation? Let's put 3 in place of x and 8 in place of y and see if it makes this equation true. That's how we can show it's a solution. We're looking at two different ways to show that a point is a solution. We can start with the x value, put it into the equation, and see if the value of y matches our y coordinate. Or we can put the x and y values both in the equation at the same time and see if when we simplify, does it make the equation true. Two different approaches that are basically the same idea for checking if a point is a solution. So let's simplify the left side. 2 times 3 is 6, minus 2 times 8 is 16, and 6 minus 16 does equal negative 10. So 3, 8 is definitely a solution to both equations, but that just confirms what we already knew, It's a point on both lines, so it must be a solution to both equations. Here's a quick example. We have two equations, and I've already made the graphs for both. Y equals 1/2 x minus 3 is this line in blue. The other one, 4x plus y equals 6, is this line in green. So what is the solution to the system of equations? We simply need to look for the point where the two lines intersect. We'd be finding the point that is actually on both lines. So it's a solution to both equations. And that ordered pair is 2, negative 2. X equals 2, y equals negative 2 is a solution to both equations. We can do a quick check. Let's put a negative 2 in place of y, the positive 2 in place of x, and see if it makes our equation true. Simplify the right side. First multiply 1/2 times 2 equals 1, and negative 2 equals 1 minus 3. Absolutely. Negative 2 both sides, so we have a solution. It made the equation true. Next, this equation, 2 in place of x, negative 2 in place of y, 8 plus negative 2 does equal 6. So it's made this equation true. It is a solution to both equations. Let's do another example. Solve this system of equations by graphing. You can pause the video to try this one on your own, and now we'll look at the answer together. First, I'll take the y equals negative 2/3 x plus 2. I'm going to make another table, even though we do have a variety of strategies, and we'll use a different strategy with the next equation, but we're still sticking with this strategy of making ordered pairs using a table. So let's let x equal 0. Substituting 0 in place of x, we have y equals negative 2/3 times 0 plus 2. The multiplication equals 0, so we're left with y equals 0 plus 2, y equals positive 2. There's our first ordered pair solution, 0, 2. When we plot the point, it is right here on the y-axis. It's a y-intercept because x equals 0. For our next point, we're not going to choose just 1 or 2 because we're dealing with a fraction as the coefficient of x, so we can choose specific values of x that will turn this into an integer. It'll make us not have to deal with fractions for our y value. The key is that we spot the denominator and choose values of x that will evenly divide by that denominator. So we could choose 3, 6, 9, negative 3, negative 6, negative 9. Any of those would be good choices for x because they will be evenly divided by that denominator of 3. So let's use x equals 3, substituting 3 in place of x in the equation. Now we're multiplying negative 2/3 times 3. If it's helpful, you could look at that 3 as a 3 over 1 to really see how the numerator 3 will divide out with this denominator 3 and just leave us with negative 2 and this plus 2, and negative 2 plus 2 equals 0. So we have our value for y, 0, and we've got our next ordered pair solution, the point 3, 0. Plotting this point, we will go to the right 3 units and not up or down because our y value is 0. So we're looking at the x-intercept. It's the point right on the x-axis because the y value is 0. Let's connect these points with a straight line, and there's the graph of our equation y equals negative 2/3 x plus 2. We'll label the axes x and y, and label the line with the equation. Now we'll graph x minus 2y equals negative 18. I still want to solve for y first, but now we'll go ahead and make the graph using the y-intercept and the slope. We need to undo this positive x term by subtracting x both sides. It leaves us with a negative 2y on the left side and two terms that are not like terms on the right side, so we'll be bringing down negative x minus 18. One more step to solve for y. Divide each term by negative 2. It will leave us with a positive y on the left side. Our next term is a negative x over negative 2. Well, we know the coefficient when we don't see it is a 1, and coefficient of negative x is a negative 1. So let's look at just the number parts. A negative 1 over negative 2 It doesn't divide evenly, but we can simplify it to become a positive 1/2. When the numerator and denominator are both negative, it gives us a positive answer. It's that rule that negative divided by negative equals positive, but it's a 1/2, so we cannot simplify it any further than 1/2. With the constants, negative 18 divided by negative 2 equals positive 9. Now that the equation is solved for y, we could make a table like we had with the last few examples, or we can observe that this form is the slope-intercept form, like y equals mx plus b. B represents the y-intercept, so for this equation the y-intercept is positive 9, and m represents the slope. For this equation it is 1/2. So here is our slope, the coefficient of x, it's positive 1/2. Here's our y-intercept. The value of b is positive 9. Remember that the y-intercept always has x equals 0. So when we see that b equals 9, we know that it represents the point 0, 9. When we use b as the y-intercept, x is always 0. So let's plot that point, the y-intercept, at 0, 9. The way we use the slope to plot other points is to know that the slope is rise over run, which basically means the rate of change. How does the value of y change compared to how the value of x changes? This fraction 1/2 means that the value of y will change by positive 1 when the value of x changes by positive 2. And we like to call it rise over run because from a point we know we can go up 1, that's the rise. The run is horizontal, so up 1 over 2, we get to another point on the line. And remember how we said that negative 1 over negative 2 equals a positive 1/2? You can see that if I try to do another rise 1, run positive 2, I'll be off of my graph. So go back and think of negative 1 over negative 2. If the rise is negative 1, that means go down 1. And when the run is negative 2, it means go to the left 2. And see that we find another point that is on that same straight line. We're just going in the opposite direction. So let's connect these points with a straight line, and now we have both equations graphed. You could label this line with either the original equation, like I did, x minus 2y equals negative 18, or you could label it with y equals 1/2 x plus 9. I'll choose to use the equation that was in this problem originally, so the x minus 2y equals negative 18. But remember, we're looking for the solution to both equations. So we're looking for the point where the lines intersect. It is right here at the point negative 6, positive 6. From the origin, if we go left 6 for the x value of negative 6, and then we go up 6 for this y value of positive 6, we see that's the point where the two lines intersect. So it is the solution to both equations. It is the solution to this system of equations. Now we end up looking at several different strategies for solving systems of linear equations. And we want to get accustomed to seeing our solution as an ordered pair that represents the value of x and the value of y. So for this problem, our solution is the ordered pair negative 6, 6. We found that point by graphing, but remember it also represents the value of x and the value of y, that if we put those values into the equation, it would make the equation true. And it would do that for each equation in our system.